All right. Hello, everyone. Kyle A0Z. Welcome to the channel. And tonight we have Carl K9LA from, I think, Indiana, right, Carl?
Yeah, Fort Wayne.
Fort Wayne, Indiana. Carl is I know Carl from Society of Midwest Contesters, SMC. We are both in that contest group. And Carl does an update on Cycle 25. You've done probably many updates on many of the cycles, haven't you?
You bet. Except Cycle 1 back in 1755. I missed that one. So.
You missed it by that much.
Yeah.
So Carl is used to work at Motorola in Chicago, and he is the ARL Central Division Director, which is Indiana, Illinois, and Wisconsin, if I can remember right. Correct?
That's correct.
Yep. Let's see. We're getting an echo on. Let me take one of the audio streams off. Thanks, guys, for the echo. But yeah. What we're going to do is we're going to do a quick update on Cycle 25. And Carl, I've seen many of Carl's slides before, and he does an excellent job on breaking down the solar cycle. And I think it'd be a good update for us to say where we were at, where we were, where we're at, and then a future what we're going to see probably in the future, and what the predictions were and actually where we're at in the solar cycle. So I'm excited to get an update. And if you guys want to put some questions in the chat for Carl, that would be awesome. And we'll ask him as he rolls through his slides. So it's all yours.
Sounds good. Okay, very good, Kyle. Thank you very much for the intro. And the first slide there, two things. Cycle 25 is near maximum, so that's why the sun is smiley face. If you're an aficionado of the higher HF bands, that's good. And down in the lower right, just want to remind everyone, don't forget the solar eclipse on April 8th. Fort Wayne's going to be in the path of totality, so we're going to have some fun. And I know Ham SCI guys are going to do a solar eclipse QSO party. And I encourage you maybe to think about doing something to learn about what solar eclipses do to propagation on our bands.
Yeah, we're going to have...
Okay, let's see if I can advance.
Yeah, next week on Thursday, we're going to have a special stream. Ward and Nathaniel are going to be on, and we're going to talk about
excellent.
And solar eclipse and the SEQP. So be looking for that. It's gonna be awesome.
Yeah, that's right. The Ham SCI workshop was last weekend in the Cleveland area at Case Western Reserve University. Lots of good presentations, 2 days, Friday and Saturday. So Ham SCI is doing a lot of good work, that's for sure.
Yeah,
okay.
Very cool.
Okay, so I went to the next slide. Hopefully you can see it.
It is, let's see, is it just behind or is it not advancing? It's not advancing.
No, it advanced on my screen.
Yeah, it didn't on mine. So why don't you get out of full screen mode and just click on the slides, because that's what we're seeing. There you go. Yep. So I think it's going to advance here, hopefully.
Yeah. Okay.
Oh yeah, there it is. Got it.
Okay. So when we talk about solar cycles and where we are and where's it going, it's always good to look at history. Now we've had 24 solar cycles. There's a plot of all 24 and what the maximum smooth sunspot number was in each of those 24 solar cycles. Cycle 1 there, way on the left, began in 1755. Our record begins with that solar cycle because everyone felt that the data was good enough to record it. There of course, are reports of sunspots and observations before that, but there just wasn't enough information recorded. So cycle 1 in 1755, and the last one was cycle 24. Now, you can see that I've annotated in red 3 cycles. On the bottom left there, cycle 6 was the smallest in recorded history. It was pretty small. And I should mention that the Maunder minimum, which you've probably heard about, occurred before cycle 1. So we don't have a great abundance of data, but we're pretty sure there actually was a Maunder minimum when there was few sunspots. Cycle 24, the last one, it was the 4th smallest in recorded history and the smallest in our lifetimes. So that was pretty small. And then, of course, there's cycle 19 for us old guys. Well, we're not old. We're just experienced. Got to remember that.
Whenever, like in history, whenever we talk about a solar cycle, it's every, keep me honest here, it's every 11 years, right?
Approximately 11 years. Yeah, they can vary from a couple of years or shorter to a couple of years longer, but on average, it's about 11 years.
Gotcha. And how do we measure a solar cycle? Is it by the number of sunspots that are visible on the sun?
Yes, we humans count them. So, okay, you got to think about that a while.
Yeah.
Just think of what telescopes looked like back in 1755 and how good they were.
Right.
And compared to telescopes today, and then again, you got humans counting. So is that little dot on the sun a sunspot? Should I count it or shouldn't I count it?
Right.
So there's lots of interpretation by humans. A guy named Wolf came up with the standard way to measure the number of sunspots on the sun. And it involves counting all the sunspots and also counting the groups of sunspots. And so there's an official way to count the number of sunspots, but still humans are doing it. And we can be biased.
Yeah. So when do you think, Carl, when do you think that we got to a point where it was consistent and it was accurate? Was it after that standard was created?
Well, the standard was created in the 1800s.
Okay.
So Wolf went back and applied that to all the observations he had back to cycle 1. So at least all the 24 are kind of measured in the same way.
Okay. Gotcha. The Traveling Ham asks, go ahead. Go ahead, Carl. Sorry.
Okay. So what you're looking at is the maximum smooth sunspot number. So we got to talk about daily, average, and smooth numbers. Of course, the daily value is just, how many sunspots are there, or what's the sunspots count each day. So if you take all the days in a month and average them, you get the average or the monthly mean. If you plot that data, it's very spiky. So what we've done is further average the monthly means, and it's a 12-month running average. And that's the official way to measure the maximum of a sunspot cycle. It's a very heavily averaged number, and it takes 12 months of data to do it.
Gotcha. Okay, very good. Makes sense. We got our first question here. The Traveling Ham wants to know, when did cycle 19 peak? We've got that largest recorded in history. And do you remember about the time frame?
Oh, yeah, late 57, early 58. 1957, 1958. I was licensed I got my novice in October 61. So I was just on the decline of cycle 19, but it didn't matter because I didn't know anything about sunspot cycles anyway and how they affected propagation. I just got on 40 meters and had fun.
Right. That's awesome. That's
ignorance.
Awesome.
Ignorance is bliss sometimes. Yeah.
Right. You were just enjoying the ham bands, right?
Oh, you bet. Oh, yeah, that's right. So what we really should take away from this plot is the fact that sunspot cycles are somewhat cyclic in nature. You can see that there have been 3 periods of big sunspot cycles, or big sunspot cycles. Yeah. Like cycle 1, 2, 3, and 4 were kind of big. And then along comes cycle 5, 6, and 7. They were small.
Yep.
Then we had another period of big solar cycles, another period of small solar cycles, another period of big solar cycles, in which cycle 19 was there. 21 and 22 were pretty big. 21 peaked in 79, 22 peaked in 1989. And then along comes cycle 24. So the big question is, has cycle 24 ushered us into the 3rd period of smaller solar cycles?
Oh,
which,
yeah.
Normally is not good for
Right.
for most of us. Now, the low band guys want few sunspots because that's less ionospheric absorption. And of course, ionospheric absorption is loss. And that does not help 160 meters, that's for sure.
Yeah, right. Gotcha. Okay.
All righty. So next we go to, oh, there we go.
Yep.
Let me know when that shows up.
It shows up. Got it.
Okay. Great. So on the left is the predictions for cycle 24. You can see there are quite a few of them, and they went from a very small cycle to a very big cycle. So
yeah,
it'd be nice if we learned something from cycle 24, but there's the number of predictions on cycle 25. And guess what? It goes from a bunch of, from a very small cycle to a very big cycle.
right.
So we haven't learned much yet. And that's because we just don't fully understand the process inside the sun that generates sunspots. We know it has to do with magnetic fields inside the sun and how plasma flows inside the sun, but we just don't have it all put together yet. So that's why there are various methods of predicting solar cycles. And you can see that with that many predictions, somebody's going to be right, right?
Right.
But there's a big question of whether they're right because they lucked out or they knew what they were doing. I'd kind of go with the former. They kind of lucked out. So whatever. Yeah.
Gotcha.
Let's see, what else can I say about that?
Yeah, it's like everyone,
You can see
got their opinion, right? And they're just throwing it. It's like a dartboard.
Yeah. Well, actually, it's different methods. For example, in the right there, you can see the annotations inside the chart. And on the left, there's physical model, spectral model, nonlinear, precursor. A precursor model seems to give pretty decent results. And what precursor model does is something prior to the solar cycle starting tells you how big that solar cycle is going to be.
Oh, yeah.
And
gotcha.
One of the good ways is how long was the solar minimum prior to that cycle, the next cycle. And there's a decent correlation, but it's not perfect.
Gotcha.
So that's one way to predict. And of course, what we eventually want to do is a good physical model that that tells what's going on inside the sun. And hopefully someday, and it may be a while, hopefully someday we'll understand all that.
Right. Got it. Okay.
Okay. Let me know when this next one comes up.
It's there.
Ah, right. Electrons are kind of slow tonight. Huh? Yeah,
They're,
okay. Well, what this is
they need a little push tonight.
Yeah, that's right. This is the latest cycle 25 data. That's the thick red curve. And it's annotated cycle 25 in progress. Cycle 25 started in December 2019. That's the pretty much the official solar minimum between cycles 24 and 25. It's when the maximum or the minimum smooth sunspot number occurred. Of course, that's also tied to the minimum solar flux and the minimum extreme ultraviolet radiation from the sun. So we have almost 4 years of data on cycle 25. And you can see that it started pretty low and eventually got to where it is.
Right.
Now, also on that chart are 4 other solar cycles. Okay, the green is cycle 24, that small one, the smallest in our lifetimes. And the X at the end of the green curve is its maximum. I didn't plot the decline of those solar cycles.
Gotcha. Okay.
Above the green is orange. That was cycle 23. And if you take the average of all 24 solar cycles, cycle 23 is pretty much an average solar cycle. So that's that. And then I mentioned cycle 21 and 22. There's cycle 21. It was moderately big. That's the blue curve.
Right.
And then, of course, I had to put on cycle 19, the biggest in recorded history.
Right.
And one of the things that you can see is the larger the cycle, the shorter time it gets to its peak. So if you apply that to the red curve, it says it's not going to be big. We did surpass cycle 24 a couple months ago. And the question is it going to kind of just stay flat until it starts declining, or is it going to make it up to an average cycle?
Yeah, it's
all we can do is wait to see what happens.
Yeah, it seems to me, for the graph, it's kind of leveled off. Do you think that some of those other ones have leveled off too, but have come back up? Yeah, so it's gonna
yes
be interesting.
Yeah, that's right. So we can't say anything about it yet. We're just gonna have to wait and see what happens.
Yeah,
but we're probably within a year of the maximum. Yep.
Oh, so you think?
I think a lot of people would like to see.
Oh, so you think the maximum's probably going to be in 25? You think?
The consensus mostly is late 2024, early 2025.
Gotcha.
Again, we're not very good at predicting that either, but well,
right.
It's the way it is.
Right. Okay.
Yeah. So cycle 25 probably will go down as a smaller solar cycle, which means cycle 26 may be a small one also, if the sun continues that pattern of several big cycles, several small cycles, several big, several small. So I may not be around for cycle 26, but we'll see what happens.
Right. Well, maybe we'll have the potion of life here soon. Who knows?
Yeah. Right. Yeah, who knows? And this is the latest data. The month of March is almost over, so I'll have another month of data here, probably in about 5 or 6 days, and we'll see. My guess it's going to stay flat at the moment, but we'll see what happens.
Got it. Okay.
Now, okay, one thing you should see in cycle 24 and cycle 23, it had 2 peaks. Both of those had 2 peaks. It maximized, then it dropped down, and then came back up again.
All right.
It's pretty obvious cycle 24 did that, cycle 23 did that. So what's going to happen with cycle 25? Well, that's what the next slide is. And let me know when you see it.
We got it.
Okay. So what I've plotted on this Excel graph is the sunspots with respect to which solar hemisphere they emerged in. Okay, so if you look at cycle 24, the blue curve is the northern solar hemisphere, and it says the northern solar hemisphere early on in cycle 24 was much more active than the southern hemisphere, which is the orange curve. Now the green dots are just the total of both northern and southern. But then towards the when cycle 24 peaked the second time, it was mostly because of activity in the southern hemisphere, whereas the northern hemisphere wasn't very active. So that's what gave it two peaks. The two solar hemispheres were not working in concert. So if you go to cycle 25, what's happening so far is the two solar hemispheres are kind of in concert, but we should keep an eye on what's going to happen in the next couple of months. There's a small divergence, but if I had to make a guess, I'd say that cycle 25 is just going to have one peak, or a very small very small dip and get to another peak.
Gotcha. Can you
best guess at the moment?
Gotcha. Can you explain, like, why is there a northern hemisphere and a southern hemisphere sunspot numbers? I guess I don't understand that concept.
Well, the sunspots emerge, in the sun, and we just determine if they're above the solar equator or below the solar equator.
Oh, you're talking on the sun. They're above or below. They're not talking about where. Yeah. Okay. I was like, what is going on? You mean, yes, on the solar equator, if they're above the equator or below the equator. I gotcha. Okay, very good.
Yeah, not the northern Earth hemisphere or southern Earth. It's the northern sun or solar hemisphere.
Yes, got it.
Southern solar hemisphere.
Got it. Very good. Okay.
Again, all we can do is wait and see what happens.
Yes.
That's all I had on the sun. If there are any questions, I'd sure like to answer them. I got some other slides about some other interesting stuff. But if anyone has any questions about solar, NOAA, NASA put out is one of the groups that put out a forecast for cycle 25 to be kind of small. Now they kind of underestimated things, and they did a revision, and their prediction is probably pretty much what cycle 25 is doing right now. Now, perhaps some of your listeners have heard of Dr. Scott McIntosh.
Yes.
He's he and his colleagues predicted that cycle 25 was going to be really big, and he predicted that in June of 2020. But they had to come back and revise their prediction down in, I think it was August of 2021, because of certain things happening on the sun that they had expected to happen, but they hadn't happened when they expected it to. So they're still predicting a cycle that's a little bit bigger than an average cycle.
Gotcha. Okay.
I'm kind of leaning towards the NOAA prediction might be closer than the Dr. Scott McIntosh, but well, we'll see.
Yep, we'll see.
Happens. Yep, we'll see. But I think I've even seen some predictions for cycle 26 already, and that's really based on the fact that cycle 24 was small. The expectation was cycle 25 was small, is going to be small. So that means we're in that period of smaller solar cycles, and cycle 26 is going to follow. So I hope I'm around to see what happens with 26. That would be fun.
Right. Yeah. Right. Okay. We talked about those cycles of big and then small and then big, and then they go in. I think you said like groups of 3 or 4 where they'll have 3 small ones and they might have 3 big ones. And
but we have to recognize the sun is going to do whatever the heck it wants to do, not what we kind of expect it to do. So
Right.
He's got a mind. The sun has a mind of its own here, right? Okay.
Right.
So anything else on the solar stuff
I don't think so.
before I move on?
Yeah, I'm going through the comments here, and a lot of comments about this is really awesome data, good data, and then let's see, people are talking about the history. It's love to see the history of all the solar cycles. Yeah. So if you have any questions for Carl and the sun, yeah, put them in the chat and we'll come back to them. But yeah, we can keep going.
Okay. Now let's get into some practical stuff for ham radio. I enjoy listening to Dr. Scott McIntosh because, he understands a lot of the physics about the sun, and I enjoy listening to him. But let's look at some stuff that's applicable to our operating. So let me advance the slide, hopefully. Yep,
Got it.
I've got it.
Yep.
Okay. So what this chart shows is for a constant smooth sunspot number, the monthly median maximum usable frequency varies depending on which month you're in. What that says is there's a seasonal dependence to the ionosphere. And what I've plotted here is a path from K9LA to DL, which is Germany. It's at 1500 UTC. And I've plotted the maximum usable frequency to DL versus the month of the year. And what you can see is there's a significant dip in the summer months, which means the maximum usable frequency that you can use, or that I could use to Germany, goes down. It doesn't vary too much on how big a solar cycle is either. It's kind of around 20 megahertz, which says 20 meters ought to be okay. Right. 17 meters is probably going to be there for quite a few days of the month. And but then when fall and winter come around, the MUF increases. And why it does that is because the composition of the atmosphere changes versus month, versus season. And it all is tied to the ratio of atomic oxygen to molecular nitrogen, because atomic oxygen is good for creating free electrons, which is what we're looking for propagation, whereas molecular nitrogen is not good for creating electrons. And the higher the O to N2 ratio, which occurs in the winter, the more ionization and the higher the maximum usable frequency.
Ah, interesting.
So what this kind of says is, we got field day coming up, right?
Right.
And what's going to happen in field day? Well, even though 10 meters and 15 meters are doing rather well right now, in the summer months, especially June, the MUF probably won't allow any 10 meters, at least via the F2 region. So we just got to kind of hope that sporadic E occurs and gives us some 10 meter and 6 meter propagation during the summer months.
Right. Yep.
Sporadic E is, summer months mainly. And late morning and early evening are the best probabilities for it. So, but, there's no guarantee it's going to happen this summer. Just hopefully it will, and it'll make field day more exciting for those out in the field.
Right. Yeah.
Let's see. What else can I say about that? Well, it just shows that the F2 region varies. It's very dynamic, and it can change, and there's lots of things that can affect it too.
Is this any reason why there is like a quote unquote contest season? Was there any relationship to that?
Yeah, I think CQ Worldwide in October and November, ARRLDX in February and March. They picked the right months, and I'm pretty sure it was done on purpose.
Right.
Because they realized that propagation was better in the fall and winter months for a worldwide DX contest. Yes.
Right. Yeah. Somebody asked me why contests are at different times and who picks whenever contests are happening. And I said, well, I'm sure that there are committees, right? And they figure out what weekends work best. But I also said, I think that some of it has to do on propagation, and I'm glad that I gave that answer because I was pulling it out of my butt, but it seems that I was halfway right. So,
yeah, well, you were pretty much right. Of course, which weekend is best? How many other contests? There are quite a few contests every weekend. It's unfortunate that field day is in the summer, but that's good because you want people to go outside. It's warm.
Right.
But it'd be better in the fall and winter. But well, we got winter field day, but that's usually we're inside doing that. Yeah, there's some guys who brave the outdoor weather and for winter field day.
Right.
And the IARU contest. It's an HF, it's a worldwide contest, and they have a problem with the summer months, and they hope that sporadic heat happens to help 10 meters and 6 meters.
Yes, so, yeah.
They're in July. Yeah,
yeah, I love that contest. That's one of my favorite contests.
Yep. Let's see what else. Okay, that's about it for that. And let me explain, our understanding of the ionosphere is not deterministic. In other words, we could take all those parameters you see on the internet, K index, A index, SFI, SN, EUV, and protons, electrons, and everything, but we can't say what's truly happening in the ionosphere on that day. What the problem is there are three sources that cause the F2 region to vary. One, of course, is solar radiation. We understand that very well. The next is the ionosphere is also dependent on what the geomagnetic field is doing. In other words, if the K index is low, or if the K index is high, that can change what's going on in the ionosphere. The third source of F2 region variability is events in the lower atmosphere that couple up to the ionosphere. For example, a volcano can cause a variation around the volcano in the ionosphere up at F2 region altitudes. So we are doing a lot of research in that area, events in the lower atmosphere, but we don't have any parameters that we could plug into a propagation model. So until we understand that, our understanding of the ionosphere is a statistical model. And that's where that word median comes in the title of that graph.
Yeah.
A median implies a 50% probability. So what that says is we have a pretty good idea of what the median MUF and the median signal strength are, but there's a range about those medians. And it says on any given day in that month, the signal strength and the MUF could be higher or they could be lower.
Does that average, does it fluctuate greatly? I mean, I understand that, if there's a volcano or if there's a solar, a storm that happens. But on any
Yeah.
given day, yeah, is there like a huge amount of fluctuation, or is it pretty steady, but we just are managing that that standard deviation?
Well, we're the the model of the ionosphere using our propagation programs is a monthly median model. Okay. And what they tried to capture is, the 50% point, and then the lower and the upper boundary. And that's all in our propagation predictions. So if the monthly median MUF is like 21 megahertz, that generally says that it could be from like 18 to 24 megahertz on any given day. But that's unfortunately how we understand the ionosphere.
Gotcha.
We don't have daily propagation models. Now, what we can do is take ionoson data and assimilate that into the model to give us more of a daily prediction. But, it's a big world out there, and there aren't a heck of a lot of ionosons, especially over water.
Yeah, gotcha. Okay, very good.
Okay. Okay. That one up now?
Yep, got it.
Okay. Something that probably we all realize is man-made noise has increased over the years because of all our electrical devices, computers, iPhones, everything. The International Telecommunications Union, ITU, back in the 1970s, measured worldwide noise. Well, okay, they measured it in certain places and extrapolated to the world. And their data showed that the noise on 160 meters in a CW bandwidth in a residential area was about S8. Okay, the noise on 20 meters in a CW bandwidth in a residential area was about S2. So one thing that says is the higher in frequency you go, the man-made noise decreases. So there's not as much noise on the higher bands as compared to 160 meters, which that's why a lot of signals are usually there. Yeah, that's why signals are kind of at the noise.
Yeah,
on 160. Now, there's some recent data just a couple of years ago from the Netherlands. They made measurements in residential areas, in urban areas, rural areas, and remote rural areas. And just comparing the man-made noise nowadays to what happened in 1970 showed that there's about 9 dB more noise on 160 meters CW in a residential area. And it increased by about 4 dB on 20 CW. So all this noise and all our electrical stuff is causing some concern here with ham radio. And that's a... We'll get into this in the next slide. That's why the digital modes are good, because they can hear signals farther down into the noise. And that's good. That's a good mitigation.
Yeah. Do you think that other countries are better at mitigating noise than like, are we horrible in the United States? But I would think like, the Netherlands and Finland and those countries over there, they seem to be very progressive, and they like to nip things in the bud before they get to a problem. Are there countries that are better than others on getting rid of man-made noise?
Yeah, probably third world countries that don't have a lot of infrastructure are probably best, but
yeah,
Europe has its problems. The International Amateur Radio Union IARU is divided into 3 regions. Region 2 is North America, South America, etc. Region 1, which is mostly Europe and South and Africa, I'm a participant in their electromagnetic compatibility meetings over in Region 1. So they have noise problems just like we do. Solar installations, solar installations. No, shoot.
I know all about solar installations. The neighbor 2 doors down just put one in, and man, is it noisy.
Yeah. So they've got the same problem. Power line noise. They got problems with power line noise. So it's not. It's a worldwide thing.
Yeah.
And remember, I said that this new data was measured in the Netherlands. So they saw a pretty sizable increase in noise from 1970. So they're having problems too.
Jody's got a question. He asks, and
Sure.
maybe we don't know the answer, but did the AM for Every Vehicle Act make it anywhere in Congress?
I believe that AM radio is staying in cars. I'm not sure. I don't know if it's a law yet, but I believe the consensus was we need to keep AM for emergency type communications.
Yeah. Got it.
So they're in cars.
Yeah.
And I've heard people in electric vehicles, some say, yeah, my vehicle doesn't have a problem, mine does. So, the installation and the design is critical.
Yeah. Yeah. There was our friend Josh just put an HF antenna. Forgot what antenna he put in. Guys in the chat will remind me. But anyway, it was in a Ford Lightning, the new electric F-150. Yeah. And he turned the engine on, and if I can remember right in the video, it was pretty quiet. So maybe good. Ford is doing some right things on mitigating noise. Oh, it's an ATAS 120. That's what he put in.
Okay. Yeah, and going to solar installations, there are some good companies and that pay attention to noise, and most of it comes from the inverters and the optimizers. So if you do the right work on those, you can tame it pretty much. But gotcha. There's still one of the major solar installers has more work to do.
Got it. Yeah.
So, whatever.
I think they probably all have more work to do. It's just it's a matter of how much, right?
Yep. Okay, here's the next slide.
Yep, got it.
Okay. And this just comes out of the WSJTX documentation, but it's a good summary of what the various digital modes offer. And what we're looking at is signal to noise limits. For example, they're all in a 2500 hertz bandwidth. That's because that's what most of those digital modes are in, kind of, I think.
Yep.
So sideband, you need about a 10 dB signal to noise ratio to be somewhere in the neighborhood of 90% intelligible.
Oh, that's interesting.
So the signal has to be quite a bit above the noise.
Yeah.
Okay. Going to CW, well, if you got a good ear and brain, the signal can be 15 dB below that 2500 hertz noise. Now that's a significant improvement from sideband.
Yeah.
You can see FT8 makes a further improvement over CW. Then you get all the way down to the whisper. It can dig way down into the noise, but of course, the more you dig into the noise, the longer it takes to make a QSO.
Yeah. But, I forget how long is whisper. Is it 5 minutes?
I don't know. Maybe one of your listeners can
Yeah,
throw that in.
yeah. I know that
Yeah.
JT65 or JT9, I can't remember which one. That one is 5 minutes. But yeah, somebody will know in the
Yep.
chat. Yep.
Oh yeah. Yep. So FT8 took off in about mid 2017, and it leads the pack in having the most QSOs, well above sideband and CW and RIDI and all that stuff.
Got it.
I
Yeah.
guess it helps with the noise increase we have. Yep.
That's interesting that FT8, yeah, is negative 21. But then I had no idea that Whisper was negative 31. That's interesting.
That's what's in the documentation, so I kind of believe it, I guess,
Right.
unless I had a typo or.
Right. Interesting. Very interesting. Yeah.
Yeah,
all right.
that is.
JT, yeah, we're learning something. JT65 is 1 minute, and then Joseph is
Okay.
JT9 is 5 minutes, right? I think JT9 is 5 minutes. One of them is very, very
Yeah,
long.
what's not on that chart is FT4, which is between CW and FT8.
Right. Yeah.
Yeah, so you get a little bit of advantage, but every couple dB can help, that's for sure.
All right, so now everyone is telling me JT9 is one is. So now I'm asking which one is 5 minutes? Chat, what's there is a digital protocol that takes 5 minutes for a QSO. That's the question, and I know that it's out there. So, question for the chat.
Could it be outside? Could it be outside WSJT?
It could be. Who knows?
One of the other ones. Yeah, who knows? There's so many.
Yes. Yeah. Interesting. Okay. Very interesting.
Well, yeah, I only have one more slide, and what it is for those who are interested, some references. They can go chase a lot of stuff on propagation and solar stuff and whatever else. Kyle, do you want? I can send you this PowerPoint.
Yeah, we could. That would be awesome. We could put it on. I could put it on like my Google Drive, and then I can link it in this this video.
Yeah, there you go.
People can take a look at it.
Do it. Yeah.
Yeah.
A lot of good information out there.
Yeah, go ahead. Sorry.
Mm-hmm.
Go ahead.
No, I'm done.
Okay, gotcha. Very good. Let's see. I'm going to actually let me highlight this slide real quick, and so people can copy and take a look at this. And if you have any questions for Carl, let me know. Let us know in the chat. Let me go to another screen here. Yeah. Let's pause here for a couple of minutes and see if there's any questions. But yeah, interesting. It's always good to know whenever you're a ham radio operator, especially whenever you are a general or above, on how the solar cycle is coming along, and what to expect, right?
Right. Let me go back to one of the early slides here.
Okay.
Yeah, this one here. Let me know when it. Whoops, I went too fast. Let me know when it comes up.
Yeah, go.
Okay. Looking at all these solar cycles, an interesting thing to do is, for 10 meters to be open, you must have a smooth sunspot number, probably around 75. So if you draw a line horizontally on the 75 line, you can see about a year ago, cycle 25 was above that, and that's about when we started having good 10-meter propagation in the fall and winter. The bigger the cycle, the more years you will have high band that propagation on 10 meters. You can see on cycle 19, You know, it it started 12, yeah, about a year before Cycle 25 did for 10-meter propagation. So, you know, the bigger the cycle, the more time, the more years you'll have on 10 meters to play around.
Right. Got it. Yeah. Yeah. It is interesting. Like, you know, the more you learn about the solar cycle and the more that you study what the values are and what the values mean, then you can you know, you might not know exactly what's going on, but you can make some good assumptions on what's going on. But I will warn you, there's nothing worse than going out to the website and seeing that the band is quote unquote closed, but then and saying, "Oh, I'm not going to call CQ or I'm not going to get on the bands because, you know, the bands are closed." Don't do that. It's amazing how you know, if there's a worldwide contest going on, and even if there's a solar storm, they're still making contacts because the you know, operators are literally forcing the band open, you know.
Well, yeah, I think it's better to say that the bands are open more often than we think.
Yes. Yeah.
Not doing anything.
Right.
Yeah.
Right.
One good way to.
Yeah. Go ahead.
Go ahead. Okay. One good way to assess if a band is open is go to dxmaps.com, and they take spots and plot them on a world map so you can see the Great Circle Path, and you can pick the band, and it'll show that there's what other people are working, and that'll give you a good clue of what's going on in that band.
Yeah, the bands are always open. It's just a matter of where they're open to, and if there's anybody on the other side, right?
Yep, and a digital the digital modes really confirm that the bands are more open than we think.
Yeah,
or at least they're more open than our typical legacy sideband and even CW stuff.
Yeah, yeah, very good. So I'm checking here in the chat for any questions. Again, put your questions in the chat because we're going to wrap this thing up. We try and keep it to an hour or less. Everyone's saying thanks for the presentation. Learned a ton. Yeah, everyone's giving kudos for the presentation. And it's yeah, this is like setting it again in my graduate level class. Interstellar Starman says citations. Thanks. Cool. And then yeah, this is definitely a good presentation. And then yeah, Scout says before you go out on a sota or a pota, I never look at the weather, atmospheric or solar. If I waited for ideal conditions, I'd probably never leave the house. Life is too short to wait for conditions. Yeah, perfect statement there.
Yep.
All right. Anything, Carl, any departing words, anything else that you want to share with us?
No, just get on the air and have fun. Right now, Cycle 25 is big enough. Get on 15 and 12 and 10 meters, and you'll have lots of fun with moderate antennas and moderate power, like 100 watts. And of course, the pota guys and the sota guys and probably iota guys, they prove that you can have fun with modest setup and take advantage of it now before Cycle 25 starts its decline and we're back down to solar minimum again.
Yeah. We're gonna go. Yeah, thank you, Carl.
Wow.
I want to. Oh, is that a kitty? I hear.
Mm-hmm.
I'm posting.
Well, we got 8 cats, so there's usually one.
There, I see a tail.
Yeah. Yeah, like I said, we got 8 cats, so you'll see them. And my biggest job is keeping them off the keyboard.
It's like shooing them away at all times. That's funny. All right, very good. Well, thanks,
Yep.
Carl. I appreciate it. Frank is up next on the YouTube.
Oh, you're welcome.
So go over and hit Frank's channel up. But again, Carl, thanks for the information. And if anybody wants to, we're going to put the presentation. Carl's going to send it to me. But if there's any way that or any need that, what is the best way to get a hold of you, Carl?
K9LA at ARRL.net.
Very good. K9LA at ARRL.net. And thanks for your service in the ARL and being a division director for Central Division. Appreciate it. And
okay.
Yeah, think we're good to go.
Okay.
We're gonna say 73s. Thanks, guys. See you later. Thanks, Carl.
73. Thank you, Kyle.